Welcome everyone to the 7th annual Johnson Creek Science Symposium. We're glad you could all make it today. We have a record number of people signed up, over 150. So we're looking forward to sharing with you 8 presentations from a variety of folks in academia, agencies, and nonprofits. So before we get started, I have a few housekeeping Zoom webinar details. Probably many of you have heard this before, but I think just in case there's some folks who this is the first time with a Zoom webinar, that it's important that we go over the housekeeping details. So let's get going. Let's see, as a Zoom webinar, which is opposed to the Zoom meetings, which many of you are familiar with. You're a participant here, an attendant. You're attending rather than being an active participant, so your box with your image and your name will not appear on the screen. And by default, we've set you up for speaker view. This means that the person speaking will appear in a large box in the center of the screen, and the other boxes will be to the side. You can change that if you want by clicking on the view icon in the upper right-hand corner of the screen. So other options are gallery view, but I recommend speaker view. Now, we are going to have a question and answer session, 2 of them, 1 for each session. And the way you interact is if you look at the bottom of your bar, anytime you move your mouse, that ribbon will appear and one of the icons says Q&A. If you click Q&A, a box will appear and you can type questions for the speakers, and everybody in the webinar will see the questions. So please feel free at any time to ask a question of a speaker. However, we're going to wait until the Q&A session to answer it. So you might want to wait until the speaker's finished before you actually answer the question, just in case they answer your question as part of their presentation. Okay, after the first session, we're going to have a 15-minute break, and we'll have this slide go back on the screen that says Science Symposium. We'll be back shortly. Be a 15-minute break, and we are recording this Science Symposium, and it will be broadcast, or it'll be placed on YouTube in hopefully less than a week. So let's begin. And what we'd like to do is launching a poll. And I'd like, if possible, to everybody watching today to answer the poll. We have a couple questions. We're going to do 30 seconds per question. And the first one asks who you are. That'll give all of us an idea about who is participating today. So are you with a university, a public agency, nonprofit, you volunteer, or other? And it's multiple choice. So in that, you can answer multiple answers per question. So I'm going to just give a few more seconds. On this, there's also a second question which asks, how many science symposiums have you been to? Is this your first? You've been to 2 or 3, 4 or 5? You attended all of them. So let's just do a few more seconds here, and then we'll look at the results of the poll. So let's see, 5, 4, 3, 2, 1. And I see one of our presenters has said, hey, there's no option for 6, and I've been to 6 of them. Okay, so let's see what we got here. The results should show up on your screen right now. Let's look at question 1. Looks like 7% affiliated with a university, 36% public agencies, 8% nonprofit board or staff member, 31% have volunteered with the council, and 29% other. And it looks like approximately 1/3 of the people, this is your first Johnson Creek Science Symposium, so welcome. We're very glad you could make it. Another third, a little bit more than 1/3 of you, second or third time. And the other third are hardcore folks that have been to 4 or more symposiums. It looks like a few people have attended all 7. So that's great. All right. Whoops, let's pull this off the screen. So we're going to, soon here, we're going to get started. And the first thing I'm going to do, scrolling through the list to see who's here, I'm going to introduce you to our session moderator. The session moderator is Katie Holzer. She is a watershed scientist for the city of Gresham. And to read her full bio, please read the program that I emailed to everyone who had signed up earlier this morning. So Katie, please take.
Excellent. Thanks, Daniel. Excited to see you all here today, and we're excited that yet again this year we have enough good research going on in the watershed that we're able to put together a full symposium. So that's always exciting to see. And so in this first session, we're going to have 4 talks with questions at the end of the session. So if you want to go ahead and write questions as the talks are going on in that Q&A, to help me out moderating, if you can put the name of the presenter or the topic of the presentation that you're addressing in the question, that'll help me sort through and figure out who to ask it to. So for our first presenter, we have Rebecca Talbot, who's a master's student in the Department of Geography at Portland State University, and she's going to be telling us about her studies of microplastics in our streams. Go ahead, Rebecca.
Okay, great. Thank you so much for the introduction. Let me just share my screen here. All right, and hopefully everyone is able to see my my slides here. But again, thank you for the introduction, and thank you everyone for being here. I'm going to be talking a little bit today about my thesis research, which involves the spatio-temporal analysis of microplastic concentrations in Portland's freshwater. So just to give you a little background about microplastics, they're considered to be pretty much any piece of plastic that is less than or equal to 5 millimeters in length. They are a growing concern in aquatic environments, and they're usually formed either through primary production, in which they're manufactured at very small sizes and are thus already 5 millimeters or less when they enter into the environment. But more commonly, they're formed through secondary production, which is just the degradation of larger pieces of plastic. So there are various forms of microplastics, and these forms can be indicative of sources. So for example, fibers often result from the laundering of synthetic clothing. And we do see some links with spatial factors. Urban land use in particular has been closely linked with microplastic pollution. These regions tend to have higher rates of plastic production and are hotspots for litter. And in addition, they tend to be sites for wastewater treatment plants, which have been found to be important delivery pathways of microplastics to aquatic environments. Previous research has also shown population density to be linked with microplastic pollution. And for instance, this might be because of increased amounts of washing machine effluent or other types of household sewage. And agricultural land use can also result in increased microplastics in our environments. And this can be due to the use of biosolids, which are often applied to agricultural lands as a fertilizer, but they also tend to be pretty rich in microplastics. And of course, we see a lot of high plastic use in agricultural regions. So plastic tarps or baling twine, things of that nature. And all of those plastics can end up back into the environment. So microplastics have also been linked with seasonality, especially with regard to precipitation. Some previous research has shown that microplastic concentrations tend to be lower in the dry season and higher in the wet season, or also after larger storm events. And this is because increased runoff can introduce microplastics into freshwater environments. Lower flow rates have also been found to lead to the accumulation of microplastic pieces, especially along riverbanks. Some research has found that there are fewer microplastics in the center of the river channels themselves. So microplastics can vary over space and time, and they are very heterogeneous within a given water body. So this figure just shows the processes affecting microplastics across a range of space and time scales. And not a whole lot of studies have evaluated the role of seasonality with regard to microplastic concentrations. It's a lot more common for them to get more of a snapshot of microplastic pollution in which they incorporate a single sampling session into their study design. So the current study is interested in examining the role that seasonality plays in microplastic concentrations, and we're looking to do this at both the river reach and subwatershed scales. The presence of other contaminants has been pretty well documented in the Portland area, but we really don't know a whole lot about microplastics. So what we were interested in finding out here was how microplastic concentrations were influenced by spatial factors, so watershed attributes such as land use or elevation, and how they're also influenced by temporal factors such as flow rate and precipitation. We were also interested in seeing what specific types what specific morphologies of microplastics are present at all of our sites and what ties we can make to potential sources. So the study area included 2 watersheds in the Portland metro area. We have the Johnson Creek watershed and the Clackamas River watershed. We sampled at 6 sites along Johnson Creek and 4 sites in the Clackamas watershed. And both of these watersheds have a range of land cover characteristics, and the majority of sites were selected to coincide with USGS gauging stations. For our data collection, we collected 3 samples at each of the 10 sites over the course of 3 sampling sessions. So the first sampling session occurred back in August of 2020. That was during the dry season, of course, and served to represent microplastic concentrations at base flow conditions with minimal antecedent rainfall. Our second sampling session occurred in September, which was the very early wet season, and we were hoping to see if there might be a first flush effect with microplastics. And the last sampling session occurred this past February in the middle of the wet season, when we were thinking that possibly microplastic concentrations would be a bit more flow dependent. And to just give you a really brief overview of the sample processing, in order to isolate the microplastics from the rest of the samples, they were first put through an organic matter digestion step with potassium hydroxide. We also did a density separation step and then a vacuum filtration step that isolated particles onto filter paper. And those filter papers were then analyzed under the scope seen in the photo there. And lastly, a subset of particles was shipped off to Oregon State University to undergo FTIR spectroscopy analyses. And this was intended to identify specific polymer types. So my data were non-normally distributed, so we ended up using non-parametric statistics. And as I briefly alluded to before, we did incorporate 2 spatial scales of analysis. So I delineated sub-watersheds in ArcGIS for each of the 10 study sites. And we also included a near stream scale, which was a 500-meter upstream buffer for each of the sites. And for the results, we found significant differences in microplastics between the August and February sampling sessions. So between the dry season and the middle of the wet season. And we saw higher concentrations of microplastics in August. So perhaps we're seeing there the accumulation of microplastics during the dry season. I had expected to see that first flush effect that I had mentioned earlier with significantly higher microplastics in September than August, but that ended up not happening. And kind of going hand in hand with the previous slide, there was a negative correlation between flow rate and microplastics, although this was only true for the August sampling session. So again, lower flow rates might have resulted in microplastic accumulation. And in terms of precipitation, we did see one correlation. We saw a positive correlation between microplastics and precipitation occurring within 24 hours of our February sampling session. And the pictures here just show the difference between sampling sessions between the dry season and the middle of the wet season. This is the Sycamore site located along Johnson Creek. In terms of land cover, we did find that at the near stream scale, which again is within a 500-meter upstream buffer, microplastics in both the September and February sampling sessions had negative correlations with croplands. So previous results have suggested that this could potentially be due to the high permeability of agricultural soil serving as a sink for microplastics. Otherwise, there were few significant results to report in terms of watershed variables. And here we get to the actual microplastic morphologies that I observed under the microscope. These are 4 of the most common types that I saw. Foams there on the left, even though that the picture makes it look a little bit hard, they're very, very squishy and they bounce back when prodded. I would prod each individual piece with a metal probe. I saw a lot of fragments, which were very hard and not very flexible. Films were much thinner. You could see that in the picture there. They're very flexible and can tend to fold over on themselves. And fibers are a little bit more self-explanatory. And I did see quite a few of those as well. But perhaps one of the most interesting parts of the study for me was observing tire wear particles. And I did see a significant difference in tire wear particle concentrations between the August and the September sampling sessions, with significantly more seen in the September session. So this might indicate that tire wear particles are being flushed into waterways at the onset of the wet season. And there is increasing research on their toxicity to fish, particularly salmon. So the influx of tire wear particles to freshwater environments is a real concern. And here we see a breakdown in terms of the percentage of microplastic morphologies found at each of the sites across each of the sampling sessions. So you can kind of see here the increase in tire wear particles between August and September. You can also see that fragments ended up being the most common type of morphology observed. And fibers, of course, were very common as well. And here we see the results of the Ftir Analyses, which were conducted down at Oregon State University in Dr. Suzanne Brander's lab. Their lab tested about 10% of our particles, which is pretty standard for this line of research. And this chart here, of course, just gives us an idea of what types of polymers existed at each of the 10 sites. So we did find that the most common polymer observed was polyethylene, which we typically see in plastic bags, so grocery bags and things of that nature, followed closely by polypropylene, which is found in lots of different types of packaging materials. So just to wrap up, again, we did see a few links with several spatial and temporal variables, although maybe a little bit fewer than I might have guessed. And the links that we did see did not necessarily remain true across every sampling session. The finding of more significant results at the near stream scale kind of emphasizes the importance of conducting local analyses and emphasizing specific point sources when conducting microplastic investigations. And again, those tire wear particles seem to be flushed into freshwater environments during the early wet season. Fragments and fibers were dominant, and polyethylene and polypropylene were the most common polymers. And this is pretty consistent with previous research. Other studies have found the same thing as well. So that is it. Here are my acknowledgments. I just want to say thank you so much to everybody for listening, and I look forward to any questions that you might have.
Excellent. Thanks so much, Rebecca. Really interesting. I know we've been hearing about microplastics a lot and wondering if they're in Johnson Creek right here. So thanks for diving into that and answering some of those questions. If you have more questions for Rebecca, please put them in the Q&A feature, and we'll have the Q&A session at the end of this session. So our next speaker is Adam Stonewall. He's a surface water specialist with the United States Geological Survey, and he's been the primary investigator for the Johnson Creek project for the past decade. And Adam's going to be talking to us about studies that they've been doing looking at turbidity in Johnson Creek.
Thanks, Katie. Can people hear me and see my screen?
Yes, it looks great.
Okay, great. So I've got a weird setup here where I'm looking this way because my screen's here, but the camera's here, but I promise you I'm paying attention. So we'll get off and rolling here. So this is a story about trying to chase down where the sediment's coming from in Johnson Creek. And this is going to be in 3 parts. The first part is going to be more of a little bit of background and introduction to some past work we've done in the USGS on sediment here in Johnson Creek. Then we'll talk about the current effort we have ongoing right now. And then at the very end, we'll have a slide or two about what's going to come in the future as far as the report and such. So as with all USGS presentations, there's a giant caveat that all of these data are preliminary, and please do not distribute these or take these as gospel at this point, and will be finalized in the future. So something to keep in mind. So to start, I want to have a very technical question to answer. Is sediment bad? And not to be glib about it, but we think about sediment and it's this naturally occurring thing that happens, in the middle of the forest where there are no people, no industry, no agriculture, and happens in places like Portland here in Johnson Creek. And I'm not trying to imply in this that all sediment is bad, but I do want to share a few quick things here. This is one of the most 5 frequent causes of stream impairment, as classified by the EPA. And we tend to think of sediment as bad because it absorbs a lot of contaminants, such as DDT and other legacy contaminants. And in fact, in the USGS, we had a 2004 publication. We looked at the prevalence of organochlorine pesticides in the Johnson Creek Basin. So if you're interested in that, you can check out that publication. But also just for fish in general, it affects them in many ways. And their ability to hunt, to find food and avoid predators, affects vegetation patterns. And so while not all sediment is bad, excess sediment and polluted sediment can be bad oftentimes. So that's why we're doing this whole project, is trying to figure out where in the basin is excess sediment coming from. We're not looking at which sediment's most polluted in this case. We've done that before. Could use an update probably by now. But we're more interested in the distribution of sediment, which is impetus for this project here. So as you saw in Becky's slides, we've got a handful of streamflow gauges here in the USGS in Johnson Creek. And just zoom in a little bit here. I'm going to focus mostly on this Gresham gauge up here towards the upstream part. But we also have this Milwaukee gauge down here near the mouth. And these 2 gauges both have some long-term turbidity data. We've been collecting turbidity data since about 2001, I think, at both of these sites. And we can use turbidity either by itself or in conjunction with streamflow values to estimate sediment by using turbidity for suspended sediment concentration and converting that into loads eventually. So in 2012, we produced a report that looked at those 2 gauges and tried to quantify the amount of sediment coming through those areas for the years of 2007 to 2010, those 4 water years. So delving really quickly into that report, we found some pretty good relationships between turbidity and streamflow in estimating suspended sediment concentration. So we were able to, as you can see by this graph, predict concentration fairly well at both locations here. And as that plays out, you can kind of figure out how much sediment comes through those gauges in any given year. And this just shows that, as you might expect, there's more sediment coming in with the downstream gauge at Milwaukee than what you had in Gresham. And in fact, of course, Gresham is about half to a third of what you see in Milwaukee typically. Looking at that on a month-by-month basis, you can see the 4 different years here. You tend to have pretty low months overall, but once in a while you have a really wet month. That's where you have these maybe 1,000 tons of sediment going by in a particular month or something like that. And for example, in this 2008 here, that's 1,000 tons of sediment for a little bit over 2,000 for the entire year. So about half the year's sediment came through in that 1 month. And you had something similar here in 2009. So the main purpose of this slide is just to show that we've got a few years of over 1,000 tons and a handful over 500, but most of them are below 500 as a general rule. So with this current study, our idea here is to have these 3 kind of roving turbidity probes that we move around the basin over the course of 4 years. And the idea is to try to track down where we're seeing more sediment than we would expect just through natural happenstance. The idea is to just collect as much data as possible from a wide area and kind of like hone in by moving upstream as we see signals and stuff like that. At each of these sites, we are establishing a relationship between sediment, concentration, and turbidity. And we started this data collection in 2019, and it will be continued until the end of the water year 2023. And then after that, we'll have a year of analysis and the report will be produced, hopefully around 2024, maybe early 2025. In case you haven't seen sediment sampling, which I'm guessing a lot of you have not, these two pictures kind of illustrate how that looks. You can either be in the creek weighing it with a little pole, and you collect a handful of samples across the creek to kind of get an average, and you put each of those samples in one giant container. Or you can do it from a bridge or some other elevated structure like a cableway to the same effect. You're still going in one section at a time, trying to get at least 10 sections and then putting those into one bottle to get the average amount. And then those are sent to a lab where we get the actual concentration values and some other data from there. A few assumptions to keep in mind with this analysis. We only have a handful of streamflow gauges in the Johnson Creek Basin, so any place where we do not have streamflow, we use a simple drainage area method to estimate streamflow. So for example, if the Gresham gauge is 15 square miles and another one is 5 square miles, we just take a third of that value at Gresham that we do have and use that for streamflow. There are occasions, of course, where instrumentation goes belly up, vandalism happens, batteries run out, things like that. Whenever we're missing data, we've used a random forest machine learning algorithm to estimate those missing data. And we also use those data to estimate outside of the period of record where we collected. So for example, if we collected at a certain location in 2019, we can use similar locations to estimate what would have happened there in 2020 and 2021. That way we have the same 3 years to look at for all these different sites that are moving around. So it's a common period of record rather than having this jumble of wet and dry years for different sites where you'd be comparing apples to oranges a little bit more. It does introduce more uncertainty, but it's worth it for the analysis. Also, we use one standard relation for sediment between turbidity and suspended sediment concentration for all sites. In the future, we may break those apart if we see some sites are different enough, but so far they're fairly consistent throughout the basin, so we feel pretty good about using just one relation for that. And also, all the values you're going to see are in what's called Formazin nephelometric units, FNU. Oftentimes you see other units as industry standards, but that's what the USGS tends to use. And we collected all of our concentrations in suspended sediment concentration, not total suspended solids. There's a whole presentation I could do about that as to why we think SSC is better, but that's same for a different day. Although we are collecting some TSS data as well as part of this for comparison. So really quickly, look at the last 3 years of data from the Gresham gauge where we have long-term data. I know there's a lot of points here, but the main takeaway is that we have 0 months that are above 1,000 tons of sediment coming through, only a couple above 500. So it's been a kind of a dry 3-year period so far for this study. And you can see that through the stream flow, the discharge data as well. If you take the last 21 years of data at the Gresham gauge, the average stream flow is about 32.5 cubic feet per second. We were down around 24 in 2019, and while our 2020 and 21 data are not official yet, they're looking like they're also well below that 32.5. So it's been kind of a dry few years here, as you're probably aware. Zooming in on the area we're concentrating on, it's mostly the upper part of the basin. So here's our Gresham gauge here in the northwest corner of this. And we kind of have this bluff road gauge here at the upper part, a little bit higher. If I zoom in to this middle part here, you can kind of see where 4 different confluences kind of all come in. North Fork from the east, South Fork from the south, I'm sorry, Sunshine from the southwest, and Badger from the south. And then this Telford Road gauge is the main gauge where you would see Bluff Road further upstream. Looking at the concentrations, these are box plots, so they show the median and the quartiles, and also some outliers for these different stations. You can see overall there's not a huge amount of variety, but Bluff Road is by far the highest concentrations that we tend to see there.
2 minutes, Adam.
Thank you, Daniel. Median value of 8.7 milligrams per liter. And you can break the loads out by the different tributaries. The main takeaway here is that if you take these 4 main trips I showed before, they account for about 60% of the sediment load, but they're about 80% of the drainage area. So we expect this 40% to be a little bit lower than it actually is. So that's kind of a question mark there. You can also parse these out by looking at the actual production of how many tons of sediment you get per square mile of drainage area. And once again, Bluff Road's the clear outlier here. There's quite a bit more. But just looking downstream at Telford, it's actually fairly small. So the question we have now is, what's going on between Bluff and Telford? Why is there not more sediment down there? And one hypothesis is beaver dams. This is actually one near Telford, which can be good sediment traps at times. We're getting low on time. So really quickly, our goal for the next year or so is to actually maintain the gauge we have now at Bluff Road, and to reoccupy the Telford gauge and also install a new gauge here at the East Multnomah farm. And our idea here is to try to get a better handle of what's going on between these 3 gauges. And then for next year, we'll look for something further downstream to explain more of the diffuse sediment coming in around there. And I know I'm getting low on time, but luckily that's the end. So I will leave it there and hand it back to Daniel and Kate. Thank you.
Excellent. Thanks so much, Adam. So if anyone has more questions for Adam, feel free to type those in the Q&A. And next up, we have our very own Daniel Newberry, who is the Executive Director of the Johnson Creek Watershed Council. And he's going to be talking about some fish passage projects on the North Fork of Johnson Creek.
Thank you, Katie. Okay. Let's see. Okay, assuming everybody can see this. Looking forward to...
Daniel, I'm not seeing anything yet.
Not seeing anything. Okay, hold on. Let's try again here. Share screen. Is this showing up now?
Yep, it looks good.
Okay. Still up? Okay.
Yep.
Looking forward to telling everybody about a long journey we've had with fish passage and results and where we're going from here. So probably many of you know that over the past 7 or 8 years, we've really been focusing on fish passage in our restoration work. And that is because in 2013 and 2014, we had surveys done of 274 culverts that showed that 75% of them had at least some level of fish passage impairment, either partial or complete. And we've kind of evolved our thinking about how to prioritize culverts, because with that many culverts, there really is not enough funding to be replacing culverts or removing them. There just isn't that much money. So how do we prioritize it, get the best benefit for fish? In a previous science symposium, we talked about how we had done these surveys and then had a researcher put all the data through a mathematical model to try to assess priorities for fish passage. Because originally, 20 years ago or so, a lot of watershed practitioners said, well, the way you do this is you look at the total number of miles above the barrier that would be opened up to salmon, and that's the priority. But really, when you figure cost in, you find that you could potentially do more by kind of balancing cost and the benefits of the number of miles of fish passage opened up. So after we did a model, researcher did a model for us in 2014, we came up with a list of 18 priority culverts. And what we found is that a couple of them were in the North Fork watershed, sub-watershed. And since 2015, when we came out with our action plan, as everyone knows, temperature has really, really increased everywhere. Air temperature, water temperature with climate change. And so we continued to evolve our thinking surrounding fish passage to incorporate climate change. And one of the things we did was we said, look, we want to find the areas of natural cold water. And if we can get a lot of partners together, we can probably manage to get some funding to free up the entire subwatershed. So as you can see in this map, the purple circle here shows North Fork of Johnson Creek within the entire watershed. This is a graph that came out in our 2014 water quality report. And as you can see in this diagram, red shows the greatest number of days where the temperature standard was exceeded. You see in the North Fork, especially in the upper part of the North Fork, the water is really cool. Even in the lowest part, it's much more cool, relatively speaking, than other areas of the watershed. So what we did is we took the 7 culverts and we created a coalition with a lot of partners, which I'll talk about a little later. And we began working on these culverts. Now, the first thing that happened was in the headwaters, the East Multnomah Sound Water Conservation District owns a headwater farm. And when they purchased it, there were 3 fish passage barriers. So the district themselves funded through their own budget the removal or replacement of the 3 culverts on their project. And this started in 2016. And just to show, I think, what is really emblematic of what partnerships can do, the directors of the district originally did not want to spend any money because they said, well, if you look further downstream, they're complete barriers and the fish can't get up here. So once we got all together and created this coalition, the directors said, well, we know that these other culverts are going to be taken care of in a few years. We will go ahead and we will invest the money on fixing the fish passage problems on our property. So just quickly moving through, starting with the upstream, they had a barrier, a culvert that was almost completely full and sometimes would block. This is what it looked like after the project was done. It was a squash culvert replacement, much, much wider. The second one was concrete culvert, which we've seen many of this type. They're way undersized and they can also fill up. In this particular case, the district said, we don't need this road. Let's decommission this road and let's just completely pull out the culvert. And on the west end, they had another undersized culvert that also needed to be replaced. And they chose a very low cost bridge, Pacific Bridge, the manufacturer. It's a kind of a modular bridge design. And this has worked very well. So after this happened, the Watershed Council, the next year in 2017, we worked with Portland Parks and Rec to get permission to replace a culvert under the Springwater Trail. This was a very undersized culvert right at the mouth of this particular tributary. And it was HDPE plastic, very smooth on the inside. So of course, during high flows, it was like a fire hose. Fish could not get up. And afterwards, we replaced it with a 12-foot diameter squash culvert. And you can see on top of it, that's the Springwater Trail waiting to be repaved. The next year, we looked at a county culvert just a little bit upstream. This is 262nd Street. And this is the start of 3 culverts, which we found would be kind of expensive to replace. And so we looked at some evolving technologies, and the technology we use is called the Flex-A-Baffle. People are probably used to baffles being made of steel or concrete that get affixed into a culvert. But what you're seeing, and this is Roy EY of Multnomah County Transportation Department, who has been really instrumental in helping us with the two county culverts we worked on getting through it. He's holding a Flexibaffle. They're very inexpensive. They can be put into a culvert with one person with a handheld drill. Over on the right-hand side, you can see what they look like up close. And after they've been installed, you can see all these standing waves in the culvert. This is during high flow. And without these Flexibaffles, this water would just be shooting through here. We did a test with a ping pong ball at one point, and before we put the Flexibaffles in the previous year, the ping pong ball would take probably 15 to 20 seconds to move through. With these baffles in it, the standing water and the little pools behind it, it took about a minute, a little over a minute. And then after the full season, we went back and we took this photograph during low flow. You can see these pools backed up. Without the pools, there'd be just a tiny trickle of water. Juvenile fish could not navigate it. But with the Flexibaffle, this is a solution that really mitigates the impacts of fish passage at both high flow and low flow. The next year, 2019, we worked on a culvert under Highway 26, major state highway. If we had tried to replace this culvert, it probably would have been a $5 million project. This ended up being a $200,000 project, so much, much cheaper. And a large part of this project was creating an engineered riffle. If you look at this picture on the left, you can see that there's a drop at the edge of the culvert. And on the right-hand side of the culvert, you see that the water is now backed up. What we did is we had a contractor put gravel, cobbles, boulders, sand to recreate natural stream channel bed, building up hydraulic control a little bit further down the stream so that it all flows. There'd be a pool backed up. There would never be a jump height again. So that was the first part of this project. The second part was putting Flexibaffles, because this is a very, very long culvert. So we have the same problem, both low flow and high flow, needing to get fixed, which was fixed by this project. And I put in this picture on the left because it gives you an idea of how these baffles are installed and really how easy it ends up being. And we like to joke that the cost of getting the permits and of doing the engineering design is much, much greater than the construction costs on these Flexibaffle projects. The last project that we did was done last month. This was at a county culvert. You see the tools pre-project getting all ready to put in the flow. You can see how really narrow that flow is. And this is a project that was done under 2 roads. So this was a super long culvert. And the county originally looked at replacing it and found that the cost was going to be over $1 million, especially because of different FEMA restrictions and some permitting. But this ended up being a $40,000 project, and that includes all the engineering design. And you can see on the right what the flow looks like once it's been backed up. Very, very important for juvenile fish. So a question emerges after this, how are we going to find out if the fish are actually getting up to the headwaters? And the Watershed Council has started to do environmental DNA testing. In the past year, we've done it first in the late fall, to try to detect DNA evidence during spawning season, and then we do it again in the spring looking for juveniles. And the really exciting thing was that at the very mouth of North Fork, and then also up near the culvert that we did this year, we had Steelhead DNA detected. We first did a DNA test about 3 years ago at the mouth of the North Fork, and we did not find any evidence of any of the 4 species. So we do this DNA testing at all the fish passage projects we've done over the past 5 years. And we've started to see some evidence of coho salmon getting past some of the barriers, and lamprey in some other areas, and steelhead in other areas. And we are going to be doubling the intensity this year because it's possible that if you just test once during a season, especially during spawning season, you could get in there too early before the fish have started to run. So we're going to be doing it at 2 different times, next month, end of next month, and then twice more next spring. So I'd like to end it just by thanking our partners and our funders. You know, I mentioned earlier the anecdote about working with East Multnomah Stonewater Conservation District and how their directors were convinced. We had the same thing with some of our other funders who were originally hesitant, and some of the public landowners hesitant, you know, why should we do this? There are other barriers, but by building this complete, you know, really big coalition, we were really able to get this done, get all 7 culverts done. Now there are a few other culverts. Most of them do not really cause much of a problem. We're looking at some of the others just in case, monitoring, because we might still need to do more work, but we're really excited to continue monitoring fish presence. And thank you to all of our funders, the district, Metro, Multnomah County, Oregon Watershed Enhancement Board, National Fish and Wildlife Foundation, Portland Parks and Recreation, and the Oregon Department of Transportation. So thank you.
Excellent. Thanks so much, Daniel. It's a lot of work all coming together to help one stretch of creek. It's excellent. So we'll move on to our last speaker of the session. If you have questions for Daniel or the previous speakers, feel free to stick those in the Q&A. And our final speaker for this session is Arun Palettica, who is a PhD student at the Earth, Environment, and Society program at Portland State University. And he's going to be talking to us about a framework he's been working on to understand beaver habitat in the creek. Take it away.
Thank you, Katie. All right. So the title of the project is Exploring Beaver Habitats Using a SETS approach. A SETS is a framework that looks at a problem from a social, ecological, and technological systems approach. We will discuss more when we get to the framework option. Well, the bank downstream is flooding. Well, damn it, that's what a beaver does. So look at the beavers that are native to Oregon. The species is North American beaver, and the beaver is the 2nd largest rodent in the world, and it belongs to the Cassidopsis family in the suborder, and it's within the order of Rodentia. Beavers prefer to build their dams usually in small or medium-sized streams with low gradient that flow through the valleys. So this is what we already know. And beavers also inhabit areas with vegetation, especially canopy for food and structure. They prefer aspen or cottonwood and willows for food. And the setting, we decided to do this study in Johnson Creek. Beavers are native to Oregon and have played a crucial role in state's history. Johnson Creek in Portland is home to the beaver population. We looked at well over 30 beaver dams between 2014 and 2019 using the USGS data. Surrounding areas are continuously being developed, so there's a lot of impervious development, creating more, surfaces that prevent runoff. I did go out in many places in Johnson Creek, and I was able to collect some remnants and some. There was nothing that could directly be observed, but there are many places where you can see that beavers have been present. The study sites, as you can see, beavers are pretty much distributed in the upper region, and then in the middle, and then the lower. There's not many, at least we did not have any data about beaver presence in the origin, in the upper origins of the eastern portions. But they are mainly around Gresham, flowing through Portland, and almost ending here at the Reed's College. And we can notice here that a lot of the development is essentially along this corridor. So the impacts of beaver population. So are beavers good or bad? So studies have shown that beaver dams are actually beneficial to the surrounding environment. So beaver dams create and support new wetland areas that are beneficial to many other species, such as fish and also plants. They also help in cooling water temperatures, and they also provide which also support cooler water towards the bottom. In Europe, a study has shown that beaver ponds contribute to self-purification capacity of polluted streams. And so what are the factors impacting beaver dam site according to literature? So the literature shows that vegetation and elevation often play a large role. So beavers prefer flatter surfaces and more vegetation, which is especially in the form of canopy. In high elevation areas, there have not been many studies, but a couple of studies have shown that beavers are often found above 11,000 feet in willow fields. However, elevation is not a factor in Johnson Creek because most of Johnson Creek is at sea level or about 200 to 300 feet above sea level. Trees are generally used for dam construction. Wood stumps under 25 centimeter in diameter were crucial, along with soft, fast draining soil that is required. And you can see a picture here, although this picture that I did not take, it's a stock image. You can see that this is how beavers destroy a tree. So important consideration here is that previously established beaver sites may show that there's overemphasizing on certain characteristics since the land has already been altered to a large extent. Between 2015 and 17, a study showed that Upper Missouri River observed newly colonized beaver segments and compared them to uncolonized sections. In another study, we can see that stream segments had relatively low gradients, also narrow channels, high channel complexity, high canopy cover, and low-lying areas that were adjacent to the stream. So we decided to look at the overall factors that influence a beaver's habitat on a social, ecological, and technological spectrum to understand what influences beavers' habitats the most. So we had two research questions. Why do beavers return to the same location to build their habitats, and how do ecological and technological factors influence their decision? So the conceptual framework revolves around social, ecological, and technological factors. And we are conducting this study at 3 different scales. One is at the beaver habitat level. The next one is the near riparian. Finally, the census block group scale. Census block group is a well-defined geographic unit for which the Census Bureau publishes data. The scope of this presentation is just in the beaver habitat scale, as the other two are still ongoing. So the data and methods, a set of ecological and technological variables we were able to determine at the beaver habitat scale. Obviously, the social variable is not available at the habitat scale, it's available at the CBG scale. Several types of GIS layers were used, such as the NLCD, which is the National Land Cover data. We also used the high resolution canopy data, digital elevation model to determine the elevation along the beaver habitats. We processed the data on ArcGIS software. We summarized the variables at 3 different scales: a beaver habitat scale, riparian scale, and CBG scale. However, this presentation focuses on habitat scale alone. And here you can see the difference between the 3 different scales. The habitat is dot, which is not moving. The riparian scale has much more area compared to the habitats, whereas the census block group is much bigger than the other 2. So what are the variables that might influence beaver habitat? So we listed a few ecological and technological variables. So ecological variables are the elevation, slope, aspect, distance from floodplain, channel width, and canopy, whereas the technological variables are distance to bridges, storm pipes, culverts, also like the land cover within 50 meters buffer and 100-meter buffer, and then finally street length. So the ecological variable results. So we looked at elevation. So you can see that the average elevation in which most beaver habitats are found is 69, and with the standard deviation of 30 meters. We see that most of the beaver dams are in around 100 meters elevation. Next is slope. We also see here that beavers prefer flatter surfaces, as most beaver dams have an average of 10-degree slope with a standard deviation of 8. And then aspect, we see that beavers typically build their dams facing all directions except west. This could be due to the direction of the sun, or generally the flow of the river. Moving on, we look at canopy within 50-meter radius. We see that beaver dams are positively related to the canopy presence. So higher the canopy, more beaver dams. And then also at the 100-meter radius, we see the same observation. And then we looked at the dominant land cover class at the 50-meter buffer scale. We see that most of the beaver dams are located to developed areas because Johnson Creek does flow through urban communities. Secondly, it's followed by wetlands. About 16 beaver dams are close to wetlands, and then we also have some agriculture areas. However, at the 100-meter scale, we have again more developed areas, but fewer wetlands, which is explained by the presence of more and more urban areas as you move out away from the Johnson Creek and away from the beaver dams. This is just a map showing what's the most predominant land cover class for each habitat at the 100-meter buffer scale. The observation here is that, as you can see, we are close to Freshwater here. We have more developed areas close to beaver dams, but as you go away from this area, you have more wetlands or agricultural classes that are more dominant. And then distance from floodplain, we see that most of the beaver dams are, of course, very close to floodplain because most of Johnson Creek is along the floodplain, the FEMA floodplain. There's only a few outliers here.
Arun, 2 minutes left.
Channel width, we can see that the channel width is generally prefer smaller width as it's easier to build dams across. The mean here is 73 meters. And then distance to bridges, we see that the average distance to bridges is about 2,200 meters with a standard deviation of 2,000 meters. Again, the distance to storm pipes, it's about the same as bridges. Distance to culverts is also about the same. The street length is does not seem to be significant here. At the 50-meter radius, we only have about a total of 14 meters length. And then also in the 100-meter radius, we only have about, the average is about 145 meters. So it's not really significant. Conclusion is that a such approach is necessary in understanding beaver's habitat. We also believe that a temporal analysis will provide insight into trends. The study is ongoing, so this is something we will look at. The primary requirements for beaver habitat seem to be slope, vegetation, stream size, but we will be looking at two other scales like the riparian and the census block group to see if other factors may be contributing. We believe that further conservation programs will benefit from the results of the study. Ultimately, when the study results are published, future work sets relationship at riparian scale and CBG scale using regression models, better sample set. The sample set here was only 30 plus. So we believe that more samples will make results more accurate. Results are expected to provide better insight into surrounding environments and how beavers interact with them. We acknowledge and appreciate the data received from USGS and JCWC. We also acknowledge the contributions. This was originally a class project, so I appreciate and acknowledge the contributions of other students. We also benefited from the resources of Vice Lab at BSU and UREXSRN, which has received grant from the NSF. Finally, some of the citations. Well, thank you for this opportunity. I really, really appreciate it.
Excellent. Thank you so much, Arun. All right, now we're going to bring all of the speakers from this first session back up, and we'll wait for them all to arrive, and then I'll start going through the questions. We have about 15 minutes for questions before our break, and then the second session. And so I will start going through the questions in the order they were asked, but moving among the speakers. Just waiting for all of the speakers to arrive. And if you have any additional questions, feel free to keep adding those in the Q&A, and we'll see how many we can get through. All right, excellent. First question for Rebecca. What do we know about the origin of these microplastics in your study area?
That is a great question. It's a little bit difficult to draw specific conclusions about actual sources, since we are able to narrow it down to specific polymer types, but trying to link that with actual sources is a lot trickier. I think that I'm kind of more able to make some types of, based on what I see at each site. So for example, at the my Deep Creek site, I saw a lot of tarps next to the water. I saw tarps in the river. So I can, relatively confidently conclude that that's the source of some of my microplastics that I'm seeing. Other sites were characterized by a lot of litter in the direct vicinity of the sites. So we think that that's probably a source right there. Or, for example, fibers that were found at our Clackamas site at Milo McIver, those might be due to more recreational activities like kayakers or hikers or things like that. But I think that future studies, it would be really interesting to address that kind of by, if you were able to, for example, take a piece of a tarp and send it for FTIR analyses and discover what exact polymer type it was, and then compare that with your microplastic particles and see if there was overlap, then you would be able to definitively know if there was, a link between the two. So it's kind of a tricky process.
Excellent, thank you. All right, a question for Adam. Is there any attempt to correlate sediment loads with anthropogenic activity? So things like road building, construction, forest practices?
Yeah, that's a good question. That's beyond the scope of our current research. And the hard part is it's easier to find point sources of sediment, where you have specific creeks coming in, or but when it gets all diffused by just general anthropogenic activity, it's a little bit harder. Having said that, we have been able to trace individual events to anthropogenic activity. So I know the Johnson Creek community has a very, what's the word I'm looking for, Katie, here? We're very well connected. Mm-hmm. When someone sees a giant spike in turbidity, we'll go out there and try to figure out the source. And there was like an elevator shaft issue this year and stuff like that. So, but I don't know if there's been any efforts to like quantify that on like an annual basis. It's more like we just find these individual cases once in a while.
Thanks, Adam. And a question for Daniel. In addition to fish passage criteria, are there efforts to design culvert size to meet a low frequency CFS recurrence flow event to help minimize risk of future washouts during extreme peak flows?
So the question is about designing culverts. Is that what the question asked? Because when we're doing our fish passage work, we certainly have engineers look at the projected flow rates at different designs, floods like 100-year, 50-year, 10-year. So when we do culvert replacements, that's absolutely part of the engineering work that goes into it. When we do the retrofits with the Flexibaffles, we have the engineers who we subcontract to, they do studies where they simulate what's going to happen to the flow at these different rates, what's going to happen to the flow coming out of the culvert at different rates of flow from like the 10-year flood, 25-year flood. And a lot of that has to do with complying with FEMA regulations, because I think, as a lot of folks listening today know, that when you're doing in-stream projects, you're not allowed to raise the flood level because of your project. So that makes it really interesting when you're doing these Flexibaffles, because you actually, at low flow in particular, you want to raise the stream a little bit, right, to create those pools behind the Flexibaffles. But that's only at low flow, but you also have to model that at high flow to make sure that you're not going to be creating any flooding. But I guess that's a long way of saying, yes, that is factored into culvert design.
Yeah, and in general, new culverts or redeveloped culverts have to be, wider than the wetted width of the stream. So hopefully for new construction and reconstruction, it won't be as much of an issue as the ones that were built in the past.
Right, and current NOAA standards are, it has to be 1.5 times the wetted width.
Right.
Yeah.
Excellent. All right, for Arun, in your literature search, was there any instances mentioned of beavers denning in banks along large channel streams, such as the Sandy or Clackamas rivers?
Oh, that's a good question. No, I did not find anything in the literature review per se. But in the Johnson Creek study, there are a couple of instances of beavers building dams in about 200 to 250 meters wide sections. But it could just be that not all of that section is fully water. It could there could be some small patches of smaller islands or some exposed land areas. Which would would have been used to construct those bridges.
Right. Thanks. All right, for Rebecca, this is talking about a bag ban. So would you speculate future similar surveys over time will reveal downward trends in plastics associated with plastic bags, as they're now much less used than they were in prior years?
That's a great question. I think that there is certainly the potential for that to be the case with our decreased use of plastic bags. I'm kind of thinking in particular of the fact that I didn't end up seeing any microbeads in any of my samples. And those tend to be less commonly seen in studies to begin with, but I was a little bit surprised that I didn't see any at all. And I do kind of wonder if that's partly a function of the fact that the Microbead Free Act was passed a few years ago. So maybe there was an influence from that. And of course, the fact that I didn't happen to see any doesn't mean that there aren't any in the streams. But yeah, I suppose that's definitely a possibility in terms of plastic bags, although I don't know what the trends will look like in terms of microplastics overall over the next few years.
Thanks.
Sure.
All right, for Daniel, this is talking about low flow and those flexi baffles. So do the flexible baffles trap juvenile fish in the pools at low flow, or is there a way for them to swim past or under the baffles?
Okay, good question, and it's one that a lot of people have asked. Typically, when you put the baffles in, you don't put, if you think of my hand here as being the baffle in a round culvert at the bottom, you don't put it exactly at the bottom. You kind of shift it over to the side a little bit, and the next one upstream will be shifted over to the side this way, so that you're actually creating a little meandering pattern within the Flexibaffle design. So the water, theoretically, the way you put it in, it kind of flows around the side at low flow and alternates so that the fish can get up. So yeah, the fish don't actually have to try to jump over the Flexibaffles, which are not, yeah, I mean, they don't have to jump over them, even though you have pools filling up maybe a couple inches or maybe all the way up. They just go around it. But good question.
Thanks. All right, for Arun, this is talking about Johnson Creek has some sections of WPA wall that have really sort of hardened the banks. Did you map and analyze impact of the stone wall segments of Johnson Creek?
No, I did not, but that's a good suggestion that I could consider going forward. Yeah, for the next part of the analysis for sure.
Okay, excellent. All right, and then a question for Rebecca. Tire remnants flowing into streams at the beginning of the wet season are bad for fish. Is the evidence compelling enough to mitigate with regulation and create market demand for green-friendly tires?
That is a fantastic question as well. It goes a little bit beyond some of the research that I personally have done for this master's project, but I know that there is a wealth of research that is being produced in the last few years regarding the toxicity of tire wear particles on organisms. So I think that that is certainly going to be helpful in moving something like that forward. I'm also kind of wondering if there needs to be research more specifically geared towards tire wear particles themselves in aquatic environments, as opposed to a study like this, which was focusing on microplastics in general. And if that research can kind of come up to speed with the, the toxic effects on organisms, I think that absolutely it would be compelling for something like that to go forward.
Excellent, thank you.
Sure.
And this question's directed towards Daniel, but might also be partially for Rebecca. Is there a concern that the flexible baffles will degrade over time and contribute to microplastics in the creek?
Good question, I guess. Becky, I'm just curious, would you consider micro rubber in the same category as microplastic? These things are made of, well, it's rubber, but I believe there might be some polymers in it too. What's interesting is the first FlexiBaffle we installed was in October of 2018. And we look at it every year during low flow, we re-examine it, and they're still there after 3 seasons. That first culvert is still working well. I mean, one screw had come a little bit loose, but otherwise they're still working. I don't know how fast they degrade. That would be something for me to ask the manufacturer, but I'll turn it over to you, Becky.
Yeah, another great question. And that's actually something that I've come across in looking at tire wear particles, because those weren't really initially on my radar when I began this research. And when I sent my samples off to Oregon State to have them analyzed using FTIR spectroscopy, their FTIR equipment can't really process, it can't really read anything about the tire wear particles themselves, just because they're made of, of something else. So it's kind of an interesting thing to see where exactly they would be categorized. I don't know if they would necessarily fall strictly into a microplastic category, as opposed to maybe just like maybe an emerging contaminants type of category might be appropriate.
Thanks. And then I think this is more of a comment for Adam. Looking forward to your future look at sediment coming from downstream sources. At present, there are, I expect, large loads coming from the unpaved roads in the Arrowhead Heights area. The roads may be paved in the next few years, so it could be an interesting opportunity to quantify how road improvements can positively impact sediment loading. And maybe that's something we could even look at with sort of grab samples during storms if there's not an ability to put a whole, probe there.
Yeah, thanks for that. I appreciate that.
All right, we've got 2 minutes left and 2 questions left, so let's see if we can get through these last 2. Rebecca, I seem to have heard a lot about the risks of microplastics for marine organisms, but not as much for freshwater organisms. Are there any unique dangers microplastics pose to freshwater organisms or ecosystems?
That is a great question. Yeah, there has been a lot of research about the effects of microplastics on marine organisms, but yeah, not a whole lot on freshwater organisms. And that does go beyond the scope of my research and of my project, but I'm not really sure about that. I think that it would be very interesting to see what the results of that might be. I think that there's currently research going on in Dr. Elise Granick's lab at Portland State that might address that a little bit more specifically. So I especially will be really interested in seeing what comes out about that, but that's an excellent point and a really good question.
Excellent, thanks. I'll read this last question. I see there's a couple things in the chat, so maybe the speakers could, or now there's a new one in the Q&A we won't have time to get to, but if the speakers can stay around during the break, maybe they can answer those questions. So I'll ask this last question to Daniel. Have you had any success partnering with private landowners to resolve fish passage issues on their property? And if this is a challenge, what do you think the main barriers for resolving fish passage issues on private land?
Well, I can tell you that in the past 18 months, getting a hold of landowners has been very, very difficult just because of COVID and some of the impacts there. But in general, I think you find that most of the fish passage issues in our watershed are on public roads. And so almost all of the projects we worked with have been with the public, other than a couple, let's see, last year we pulled out a dam on private property. I would say that just in general, we have done several projects with private landowners. We did that big project on Mitchell Creek a few years ago. That's not exactly a private landowner, it was a school district. So somewhere in the middle. We did a project this year with a private landowner. And, just in general, once you can get a hold of them, we haven't really had people resistant to fish passage, especially since we raise the funds through grants to do the work, and it's not a financial barrier on people. So I don't know if that answers the question.
Thank you. And if people have more questions during the break, the speakers can continue to monitor the chat or the Q&A. Thanks to all the speakers. It's great to hear about potential pollutant sources and some good things that are going on. Beavers coming in, culverts getting removed as the stream gets restored. And Daniel, do you want to say a word before we go to break?
Yeah, so we're having a break now. We're going to start again at 2:30. And we have one more session. We have 4 more speakers, and we're going to end at about 3:40, somewhere around there. So if you want to take a break now, everyone, please feel free. Katie has generously agreed to moderate any additional questions that might come up. But I want to say thank you, Katie, for being our session moderator. Bruce Newton will be the session moderator for session number 2. So thank you. Welcome back, everybody. Hope you had a good break. Once again, this is the Johnson Creek, 7th Annual Johnson Creek Science Symposium. My name is Daniel Newberry. I'm the Executive Director of Johnson Creek Watershed Council. I'd like to welcome you back. And for the folks who were not here for the first session, welcome. We have 4 more speakers, and we're going to get started soon. But before we do, I would like to introduce, or actually before I do that, let me back up. This is being recorded. So in about a week, maybe less if we can manage it, this will be put up on YouTube, and I will be sending a link to everybody who's registered. So if you'd like to pass it along to friends or colleagues, please feel free to do that. Our session moderator for session number 2 is Bruce Newton. Bruce is a member of the Board of Directors of Johnson Creek Watershed Council. Now retired, Bruce was the director of the West National Technology Support Center for the Natural Resources Conservation Service. So Bruce, take it away.
Thank you, Daniel, and welcome back, everyone. As Daniel mentioned, we're going to have 4 speakers, followed by a question and answer session. And just a couple quick reminders. If you want to ask a question, please use the Q&A button and not the chat button. Please identify which speaker your question should be addressed to. And you might want to hold off typing in your question until you get to the end of the talk in case the speaker addresses your question. So our first presenter is Julia Bond. Julie is an environmental specialist with the City of Portland's Bureau of Environmental Services. She's going to be talking about a very serious impending problem related to the emerald ash borer. Take it away, Julia.
Great, thank you. So can you hear and see everything okay?
Yep.
Wonderful, thanks. So before I get started, I just want to take a second and acknowledge my partners who have been instrumental in this work. Dominic Mays and Monty Matson. I may be presenting, but none of this work would have been possible without them. So the emerald ash borer, it's a metallic wood boring beetle. And it is interesting for us today in terms of our topic of conversation, as it is a host specialist. It is really predominantly dependent on different ash species, so this genus Fraxinus, and it's originally from East Asia, where it is a minor pest, for the most part infesting only stressed ash trees and causing some small amounts of problems. But as you all are familiar, when species move to another location, as the emerald ash borer has done, we've started seeing it in North America. It is instead quite a substantial issue where it infests not only stressed ash trees, but also healthy ones as well, causing some major issues and loss of tree canopy. So in terms of distribution and dispersal, it was first detected in the Midwest back in 2002. And since then, it has really spread out across the eastern portions of the United States. The most western detected location is Colorado at this point in time, but the general consensus is that it really is only a matter of time before we see emerald ash borer out here in the Pacific Northwest. And normally, naturally by itself, a species like this wouldn't be able to travel all that far, but it is assisted by humans. The movement of wood products from one location to the other brings the insect along and allows it to colonize and infest in a new location. So the impacts of this particular species, so far in North America, we've already seen hundreds of millions of ash trees killed so far in both urban and non-urban environments, as you can see in this photo example here. Beforehand, you had a nice, healthy, robust ash canopy. The emerald ash borer comes in and just completely decimates all of the trees in the location before it moves on to its next spot. This has implications for obviously our urban forest, but our natural areas as well, impacts to ecosystems. And then for our topic today, some of the potential impacts on a stream system for water quality, specifically temperature impacts associated with loss of ash canopy in a riparian area. So thinking ahead, there has been some work looking at and inventorying ash trees in our area. So looking at street trees and parks, but there hadn't been any work so far looking on private land and specifically natural areas, particularly as they relate to riparian areas. So that really is the focus of the work that we are doing here and what I'll be presenting on. So our local species of interest is Oregon ash. As you can see on the left, it doesn't have a huge wide range. It's something that we see throughout the Pacific Northwest, and it's really quite common in low elevation areas in the Willamette Valley, and a tree species that we see regularly here in the Portland metro area and is common to many of our riparian areas. So this is it's our one native ash species here. So it really is our species of concern that if the emerald ash borer comes in, the potential loss of this entire species from our region is entirely possible. So for our research, as I mentioned before, there's been some work looking at the abundance of ash throughout the area, but really focusing on natural areas here, and specifically the contribution or what's the composition of the riparian canopy that is composed of Oregon ash. And then consequently, if or really when the emerald ash borer arrives, what might happen to that canopy and consequently potential impacts to water quality. So we looked in two locations, the main stem of Johnson Creek and also the Columbia Slough. Today, I'll just be focusing on the Johnson Creek component, but do keep in mind that we do have some other information very similar for the Columbia Slough as well. So main stem, looking at the abundance of Oregon ash. And so starting with our field methods, our field cruised throughout the summer of 2020, and we're evaluating the abundance of Oregon ash within the riparian zone, specifically in 30-meter quadrats that were directly adjacent to the stream. So running parallel and then 30 meters perpendicular to the wetted edge. And thinking that we may not have a uniform distribution of ash throughout that entire 30-meter band, we split that up into 3 separate 10-meter sections, each one parallel to the creek, to look at characterizing the abundance of ash. So what proportion of the canopy within each one of those bands is composed of ash. And we collected a whole bunch of other information as well, but the focus today is on that overstory and what component of that, how much of that is composed of Oregon ash. So if you think about looking up and looking at the tree canopy within those different areas, and then looking at which components of those or how much is composed of Oregon ash, and then we've combined that with a GIS analysis to look at the overall distribution across the watershed. So in terms of area that's been that we were able to sample, really did quite a thorough job last summer and getting a little over 5% of all of our riparian areas being surveyed, both actually in the slough and in Johnson Creek. So as you see, the blue lines are the streams, and then the green dots are the locations of those different quadrants that were sampled for looking at canopy abundance and Oregon ash distribution. So really quite a wide range from one end of the watershed to the other to help us characterize and use that information to extrapolate for the rest of the watershed to see generally what kind of abundance we might see. So in terms of the results, this is looking at how much of the existing riparian canopy is composed of Oregon ash. And as you can see here, we've broken it out in two directions, so west versus east, and you can think of, say, the Portland city limits as really being the divider between those two. Then between the North Bank and South Bank, because that has an impact on riparian shade. And then dividing that out again by those three different bands. So 10, the darker blue being closer to the stream, lighter being further away from that. So trees closer to the stream have a more direct impact in terms of shading of the surface area of the water than those a little bit further away. And what you can see when you look at the breakout, which is interesting to look at, is that we have a greater abundance typically of Oregon ash closer to the stream channel than we do as we move further away. And generally the proportion of the riparian canopy east, so as we go towards Gresham and further east than that, tends to have a greater abundance of Oregon ash compared to what we see towards the west. And overall, when you look at the whole watershed, that shakes out to about 16%. So about 16% of our current existing riparian canopy is composed of Oregon ash trees. And when you can look at that in terms of total canopy area, again, broken out in the same way, east versus west, north and south, these are acreages. So you can see the total riparian acreages. So, but remember, these are those 30 meters next to the stream. And then specifically the abundance of Oregon ash, if you wanted to look at that in terms of total number of acres for east versus west in those different locations. So then the next question, when we have a sense of how much Oregon ash is present within the watershed, is what might that impact be to the stream itself in terms of water quality and specifically thinking about shade and temperature. So we looked at that using a model, using the heat source model and specifically the shade model used by Oregon DEQ to look at effective shade. So this is the amount of incoming solar radiation that is blocked by the stream side vegetation, so blocked by that riparian zone. And it gives you a sense of how much solar radiation is reaching the stream and therefore how much potential warming might indeed happen as a result of that. And it's the parameter that Oregon DEQ does use in many of their temperature TMDLs, including that of Johnson Creek. So in terms of looking at these different shade scenarios, we've got the effective shade over here on the left, going from 0, so that's complete solar exposure, bright sunlight. If we were to go up to 1 or 100%, that would be complete darkness, absolutely no sun reaching the surface of the stream. And then the stream moving from left over here at the mouth, moving upstream as you go to the right. And so the shaded area represents what's possible. If we were to have a full, mature riparian canopy everywhere, how much shade could we really actually even expect? So this gives us that upper threshold of what really might be possible. And you can see, depending on where you are, as you go further up, as the stream narrows, it's possible to shade it more than further towards the mouth where you would have less shading potential.
2 minutes, Julia.
Thanks. Now, the light color that you see is, again, this is modeled, and this is based on the 2019 LIDAR. And this is the current conditions. So what our streamside vegetation is currently providing in terms of riparian shade. And you can see it's variable in different locations, but there are spots where we start moving up quite pretty close to potential, versus other locations where we really are missing a lot of riparian vegetation and aren't quite up to that potential location. So then the question is, if we were to lose that 16%, if we were to have a complete loss of that entire ash canopy, which would be quite likely if we had the emerald ash borer come in and no management and replacement that came in after that, that would be this orange scenario that you see right here. So you can see there's some locations where you would have a slightly bigger impact versus others where it would be a little bit smaller. And that turns out to be somewhere between a 5 to 10% increase in the solar loading that would be reaching Johnson Creek, which may not sound like a lot, but keep in mind, if you heard Daniel's presentation earlier this afternoon, we're already talking about a stream that's incredibly warm and one that really regularly exceeds the water quality standards for temperature. So any additional heat is going to cause additional stress for our aquatic organisms. So altogether, the findings of our efforts here is seeing about 16% of that existing canopy is composed of Oregon ash. And when you look at that by acres, that would be about 3 of our existing 18 acres being lost in the event that the emerald ash borer came to town. And that would likely result somewhere in a 5 to 10% increase in solar loading. Now, one of those key remaining questions that I'm going to just leave you with here right now is, thinking about management and thinking ahead, what sort of species could we plant instead? Thinking about riparian restoration projects and things like that. And so lastly, I just want to say a big thank you to all of the folks who helped with this. Getting access to private land, the Johnson Creek Watershed Council was instrumental in this, and all of our different partners. It would not have been possible with all of your assistance. So thank you very much.
Thank you, Julia. Very interesting talk. Our next speaker is Jason Maxwell. He's a senior research associate at the Ramirez Lab at Reed College, and also with the Digital City Testbed Center at Portland State University. And his talk will be about legacies of inequality, uncovering connections between historic socioeconomic inequality and urban forest health in Portland. Take it away, Jason. And Jason, you're muted.
Apologies. Thank you for finding me there. Okay. Thank you all for having me very much. I appreciate everyone's time and attention. And let's see if I can move this a little bit so I can see better. Okay. So yeah, my name is Jason Maxfield, as was just introduced there. And my talk today is kind of wide ranging. I'm going to cover a lot of ground and do it fairly quickly. I'm going to introduce a fairly large project that I'm a relatively small part of, give a big overview, and then focus on the work that I'm specifically involved in that is most relevant to today's talk. So this is a part of a large why can't I switch slides? Oh, here it is. Okay, sorry. This is a large multidisciplinary project with folks from Portland State University, Reed College, and Washington State, Vancouver, and contains a large team of plant physiologists, social science, people that work in urban studies, hydrology, and do some biophysical modeling. And this falls appropriately under a National Science Foundation grant for coupled natural and human systems, which is looking at approaches to understanding the relationships between biological systems health and human health in various contexts. So to situate this study a little bit, what we're trying to do is build on previous work that has established some key relationships in urban forests. Specifically, there's been a lot of literature in the last couple of decades looking at the distribution of tree canopies across cities, has shown an unequal distribution that correlates with socioeconomic status of neighborhoods, as well as some work that has been done by various research groups around the country, but Vivek Chandas's lab at Portland State is one of the leaders in this, and he's part of our research group looking at the distribution of microclimate heat across cities and how infrastructure and urban tree canopy contributes to variable heat across canopies and how that can impact human health. So to build upon those previous frameworks of looking at tree canopy and heat in cities, our central question was to look at how tree health is also distributed across cities and how that can be a recursive relationship with human health. So for a variety of reasons, tree health may vary substantially across cities due to unequal maintenance, investment of resources, as well as more appropriate or more intentional planting decisions in higher socioeconomic status areas in cities. And this is an important part of the relationship because all of the key services provided by trees, as well as the risks to infrastructure, are mediated by the health of those trees. So healthy trees capture more carbon, more stormwater, provide more canopy, and are also less likely to drop branches or to fall onto cars or power lines or houses. So the positive and negative impacts of trees depend on the health status of trees, which is why it's important to understand the distribution of tree health, not just their abundance in cities. So we studied 2 transects across northeast and southeast Portland. The 4 southeast neighborhoods fall within the Johnson Creek watershed, although this project wasn't designed to focus specifically on the Johnson Creek area. A lot of our data is directly relevant to these areas as well. So our social science team developed this typology framework for understanding Portland neighborhoods. And this is still a work in progress. They're doing deeper analysis into some of these socioeconomic drivers. But because trees are long-lived organisms, they live for decades, perhaps centuries, the urban canopy that we experience today is not the result of our current decisions and current planning decisions and values, but rather as a result of the decisions made decades ago and the values decades ago. So the social science team is very interested in looking at these longer term relationships and the planning decisions made in the past. So they're doing a deep dive into pulling planning documents from city council and neighborhood meetings going back decades, as well as looking at actual budgets of investment in parks and natural areas and so forth. So they've created this framework where we have essentially these end-member neighborhoods looking at these 4 typologies in a historical lens. So we have neighborhoods that have historically and currently been advantaged neighborhoods with high investment, city resources, but also higher socioeconomic status of the residents in those neighborhoods. At the other end of the spectrum are neighborhoods that have been disadvantaged historically and currently. And then in between are these 2 categories of neighborhoods that have kind of flipped places, where you have neighborhoods that were historically disadvantaged but have experienced gentrification in the last few decades, so change in socioeconomic status of residents, as well as presumably increased investment of resources. And then neighborhoods that have seen a decline in socioeconomic status over the last few decades that were previously higher investment, higher socioeconomic status neighborhoods. And so we have 2 examples of each of those neighborhoods for our first field season. This is, I should say, is year 1 of a 3 field season, 4-year grant. So we'll have 2 additional field seasons coming. We looked at 4 large tree species across Portland: Western red cedar, Douglas fir, big leaf maple, and Norway maple. Those were chosen because those are 4 of the 5 most common large trees, according to our tallies of various inventories that we could find. The actually 4th most common tree is black cottonwood, but that's not well distributed across the city. It tends to occur in wetland and riparian areas, and it wasn't distributed in the neighborhoods of interest for us, so we did not include that. We roughly divided our sampling between parks and street trees, but we adjusted based upon the actual distribution in these neighborhoods. For example, the King neighborhood has no parks at all, so we sampled only street trees there, and otherwise adjusted occasionally based on the distribution in the neighborhoods. And I want to mention a lot of the data I'm going to discuss looks at the effect of the heat events we had this summer, the heat dome events, when we had heat temperatures that had never been experienced in the history of these trees. The 100-year-long trees have never been this hot. We've never recorded temperatures like we had this summer in Portland. We began our data collection about 8 days after the hottest time, so long enough for scorch effects to appear on the leaf from that event. So I'm not going to say too much about all the things we measured here, but I'll give you an example. This photograph here shows us working along Northeast Sandy Boulevard, doing some pretty gnarly urban ecophysiology between the highway here and freight train going by. looking at this big leaf maple here, trying to collect some data. So broadly speaking, we kind of divided the data that we collected into 3 major categories. We measured the basic physical characteristics of the tree, the size, the canopy properties, major signs of damage, etc. We measured a lot of factors about the context of these trees, so the ground cover nearby, the competition from other trees, presence, absence of things like pavement and buildings and evidence of watering, and also the temperature on a very local level at these trees. And then we did a suite of measurements of basic physiology. So looking at the photosynthesis machinery and activity, the gas exchange, and some of the stress signs of photosynthetic stress on the tree. We also assigned a general health rating of good, fair, and poor to each tree in order to check just relationships with the ratings that were assigned by volunteers that did surveys for Portland Parks and Rec previously. So for just a basic rundown on our initial findings, this was all done in the last couple months, so we're still cranking through the data and trying to understand what we found. But we saw a high variability in canopy dieback according to neighborhood type. So the more advantaged socioeconomic neighborhoods that are presently advantaged, experiencing higher investment presently, had substantially less dieback and damage and missing canopy in trees. We also confirmed, detected additional signs of neighborhood temperature variability, so several degrees Celsius difference between different neighborhoods. There was also highly variable watering. So the historically and contemporary investment neighborhoods were much more likely to experience for individual trees to be watered in those neighborhoods, whether park or street trees. We also saw that park trees were more likely to be watered, as well as western red cedar were substantially more likely to be watered than other species. We detected leaf and needle scorching from the heat damage in all areas. It was ubiquitous across the city. However, somewhat surprisingly, it was more common in western red cedar as well as in parks and for watered trees. So that was really surprising. We found that watered trees sustained more scorching damage during the heat events this summer. And other than that, however, there was no major health differences by neighborhood, which was kind of surprising to us. We didn't see substantially less healthy forests in these neighborhoods with less socioeconomic status and investment of resources. However, this leads to some kind of interesting hypotheses about why this might have been possible. One reason for this we've been toying with is that we might be seeing an overall more resilient forest in some of these lower investment neighborhoods. So the trees in these neighborhoods might have experienced through their life history less investment of resources, less watering, and higher temperatures, according to this micro temperature data that we have. And so that more stressful history over decades may have acclimated these trees to be more able to withstand the stressful heat events we saw this summer, where some of the trees that had received higher levels of care in the higher investment neighborhoods may have been more vulnerable because they depended on that level of care and thus were not acclimated to the stress conditions. Another possible cause of that is that what we're seeing is the effect of a long-term selective culling, essentially. So in the lower investment neighborhoods, trees that are stressed or damaged might be more likely to die in the first place or to be removed by managers because they're less concerned with maintaining canopy in those neighborhoods. Well, on the other hand, trees that have received damage might be more taken care of, more likely to be treated with water, et cetera, and kept alive in the higher status neighborhoods. So the effect of that over decades would be the accumulation of more vulnerable trees still remaining alive in some of these higher investment neighborhoods. So those particular
Jason,
trees,
2 minutes.
Thank you very much. Those more vulnerable trees that have been kept alive in these higher status neighborhoods may be the ones that individually experience higher damage from the heat event. So we're trying to untangle some of that in our data. And as we look forward, we are doing additional analysis to understand some of these factors, as well as pulling satellite data to understand how the spectral signatures of these individual trees correlate with the on-the-ground data that we collected, with the goal of using the spectral data going forward to do more large-scale monitoring and make predictions about tree health based upon the relationships that we see, as well as conducting more granular socioeconomic analysis to look at the residents directly around these individual trees rather than treating the whole neighborhood as a unit, because neighborhoods are large and contain a lot of variance within them in terms of socioeconomic status. So we might see more robust relationships with a more granular analysis. And beyond that, we're planning future field seasons and inviting cooperation with other folks in the management community for looking for ideas to improve next 2 field seasons. Thank you very much. Appreciate your time.
Thank you, Jason. Our next speaker is Julia Michaels. She's a visiting assistant professor of biology at Reed College, and her talk is titled "The Biggest Lab on Campus."
Hi, everyone. Can you hear me?
Yep, you're coming through.
Right. I'm going to share my screen. Just a moment. And I have to start my slideshow. All right. Hi, everyone. I'm Julia Michaels. I am teaching in the biology department at Reed College, and I am here to talk about some lessons that I've learned from running a hands-on field course in restoration ecology at Reed College for 2 semesters. It's been a really incredible opportunity, and I'd just like to thank everyone in the biology department at Reed for, for inviting me to come, and also to Johnson Creek Watershed Council for inviting me to talk today. So, where did I come up with this title? This title came from an article about our course that was written by Katie Pelletier last semester. And, we were talking and she said, well, basically, because you are using the Reed Canyon as your lab, you have the biggest lab on campus. So that is, how we sort of came about talking about it that way. And it was a really exciting course to teach in the spring because we were able to run it in person, despite all of the challenges of COVID, and doing it from a sort of social distanced and safe way, which allowed us to explore the concepts of restoration ecology together, and also the students to sort of learn in an environment outside of Zoom, which was a really great thing. And it's been wonderful to run it again this season in the fall when the seasons have really changed and we're faced with a whole bunch of other challenges. So I'm going to talk about a little bit about both of those. So as you are all aware, ecological restoration is really sort of a 3-legged stool. There's the theoretical framework behind what we do and why we do it. There's the toolbox, which is sort of the restoration strategies that we use, things like specific tools for managing invasive species or plant propagation, soil restoration. And then there's, of course, the social system that we are working within, and that includes understanding the policy and legislation, the values, attitudes, and preferences of stakeholders, and how to work within budgets and allocate resources efficiently. So these were all things that I really wanted to impart upon my students who are interested in going into the field of ecological restoration. So in terms of the course goals, we had 4 major course goals. The first is to really connect foundational ecological theory to restoration. So some of these theories that you've probably interacted with, disturbance theory, island biogeography theory, if you think back to your ecology classes, how do they inform restoration, and how do our restoration projects improve our ecological theory? So that is something that we do a lot in lecture, is talking about that. But then, what I'm mostly going to focus on today is the field-based part of the course. So we have 2 sections of a 4-hour lab once a week in which we are doing field-based data collection, analysis, and hypothesis testing. And for a lot of our students, this is sort of their first time being exposed to the whole process of coming up with ideas, finding out how they can address those restoration questions in a scientific way, collecting data and analyzing it. And then, of course, balancing ecological, economic, and social trade-offs in goal setting is something that I really want to give my students practice doing. So we do a lot of coming up with different potential ideas and looking at all of the pros and cons and talking with stakeholders, and we'll talk more about that as well. And then finally, science communication. So we have 2 stakeholder meetings per semester, one in the beginning and one at the end. And I'm going to invite you all to the final stakeholder meeting at the end of this semester. Okay, so in lecture, we're really focusing on the theoretical framework and the social system. And I use 2 textbooks that I find to be incredible resources. If you've never read Karen Hall's Primer of Ecological Restoration, it's a quick read, very sort of straightforward, and it came out just in 2020. So It's a really, the chapters are only 10 to 15 pages long. I also draw from the Foundations of Restoration Ecology, which is a fantastic textbook by Margaret Palmer, Joy Zedler, and Donald Falk. So again, in lab, we're really practicing that restoration toolbox where we might even test out some of these different, restoration strategies that we talk about. And of course, the social system is pervasive throughout anything that we are going to be learning about. So, one of the benefits of teaching this course at Reed is we have access to the Reed Canyon, which is at the headwaters of Crystal Springs, which is part of the Johnson Creek watershed. And this canyon has undergone an enormous amount of restoration already. So Zach Perry, who is the grounds manager at Reed, has been very involved in restoring the canyon, but there's still a section that has not been restored. And that is up here by Crystal Springs. It is a privately owned property owned by the Ritmenis family, and they generously gave us access to the property for this class. So what we have is this wonderful reference system where we have, restored, riparian and wetland area to sort of learn from, and then a non-restored area for us to, really brainstorm about what we can do to improve it. Here's an aerial view from Google Maps of the Ritmenis Pond area. This pond is not a natural pond. It was actually dug out by the Ritmenis family about 40 years ago and has become a very important, body of water for bird species. We also have stickleback and some other fish species in there as well, utilized by the beaver as well as the coyote. So, the first part of our class is just learning about the site history. So we talked to Zach, we talked to other people who've been involved in the Reed Canyon restoration, we read through historical articles, and then we do a lot of, walking around and understanding just firsthand these ecological dynamics that we are working with. Our first project is actually to make interpretive signs for the canyon. So if you walk around the canyon in the next few weeks, you're going to see these QR codes everywhere. And what I did was ask the students to, each pick a story, a restoration story from the canyon that they found really compelling and write about it. And so now when you walk around, you can learn a story about the restoration of the canyon. So this was a way for us to sort of start to engage with how restoration is done and think about the story that we want to create through our restoration. The next thing that we do is habitat delineation. So we actually have the students break out into groups. I give them a general idea of what habitat they're going to be, monitoring and restoring, but then I let them do the delineation themselves. So they walk around, they use, GPS apps, we use ArcGIS online, and they actually sort of, figure out the boundaries of their own habitat. And we talk about how this is a very important part of restoration. And as you can see, there are 2 labs, so there's 2 slightly different delineated habitats. This is from the spring semester. And then it's time for them to come up with a monitoring plan for each of their habitats. So one thing that's really fun is, I really allow the students to follow their own interests. So all they have to do is monitor one plans are going to feed into a restoration plan later. So, for example, if you are working in the wetland area and that there's a lot of canary grass, perhaps you'll want to do a monitoring plan that involves vegetation monitoring. Or if you're in the upland and you're concerned about the birds, to involve doing bird observations. And we learn a lot about how you take a site and divide it up into different habitat units. And that's, something that they do. And then decide how to sample either systematically or randomly using transects and quadrats, which we've had some examples from other talks about as well. So here's just some photos of monitoring. This is looking at canary grass cover. We also had a remote lab. So we had students who were unable to attend campus because of COVID. And so we put out trail cameras for them to monitor. And they were able to see, what wildlife visited the sites even when our lab couldn't get to campus. And we captured a lot of really fun footage. I don't have time, I don't think, to play this, but we have a lot of great coyote videos. And also, beaver, nutria, birds that we captured. And they even use this to do some quantitative analysis as well. We're not going to watch the video, sorry. And, reptiles and amphibians as well. Here's just some photos. We had students who were interested in insects and they were doing pitfall traps. We have students who are very interested in fungi, looking at what types of saprophytic fungi were present in the uplands. And we had a lot of students who are really interested in the soil quality. So looking at soil nutrients, soil acidity, and here's a very creative solution one student had for doing many soil tests at once. She just used an Amazon cardboard box instead of a test tube holder, which I thought was kind of fun. Some students, when they need to identify plants, will use our herbarium, which we have access to. We're very lucky. And we also have students who are focusing on the aquatic species in the pond. And so all of this culminates in a monitoring report in which students really show what they found. And they actually run this by stakeholders to say, here's what we found at the site. What does this make you think about in terms of what you would want at the site? Now that we've taken inventory, what potential do we have to restore the site? Here's a cool density graph that the remote students did, where it's based on the behavior of different bird species over time. So from the camera traps, they showed which species are interacting with one another, which species are more active at night. We also had a really interesting thing that we observed where the pond started to shrink, and it hadn't shrunk really in 40 years that the Ritmenis Pond or the Ritmenis family had been involved in it. So we were trying to figure out what is causing this pond to recede, and is it turning into a wetland habitat? And if so, should we be restoring for an open water habitat or for a wetland habitat? So this group actually ended up coming up with 2 separate restoration plans based on the potential for it to be either a wetland or an open water habitat.
Julia, 2 minutes.
Okay. Finally, we had some students who were interested in soil compaction, and this was so they could figure out what species of plants to plant. So they walked along transects from the art building down to the pond, and they found that as the latitude increased, the soil compaction decreased. We also had a student who was really interested in collecting coyote scat and dissecting it, and from that was able to food web, where we found out that actually the coyotes were controlling the nutria population, which we didn't know previously, playing such a vital role in keeping our nutria population down. We also had management trials. So once they started to collect that data and think about some of the things they would like to do for restoration, we talked about how important it is to turn every restoration project into a potential experiment. So rather than just sort of removing canary grass in several different areas and not using the same method time, we had them do it in a systematic way, where they tested out different strategies of full removal with a shovel versus pulling versus mowing, and using replicates and doing it at similar sites so that we could actually learn from that data the next semester. So here's an example of one of these sort of small management trials that the students left for the fall semester students to collect data on. We also purchased some plants from a local native nursery and tried planting with and without mycorrhizal inoculation. And then our final product was a restoration plan, which was about 75 pages, even longer actually, which includes our monitoring report and a design plan for each of the habitat sites. And so, for example, here's the wetland habitat for one group, where they've colored the areas by priority in terms of where they would suggest removing the canary grass first, taking into consideration that they found that the coyote were using the canary grass as the nesting area. So how can they remove the canary grass without disturbing the coyote population too much during the times when they're having pups? They also came up with these very detailed restoration timelines, thinking about every step and how you would plan it out over 5 years. They also got to do budgets. So thinking about, the cost of these projects and trying to keep them low, they did a low budget and a high budget to think about, what they would do if they got a grant versus if they were sort of scrounging together money from donors, et cetera. Here's another example of, one in which a group divided their habitat into different zones and then came up with separate goals depending on the zones over 6 years. So anyway, all of this is to say that we are, going to be presenting the final product of our second semester of this course on December 9th. It's going to be a Zoom presentation, and the students would be very excited to have you there. So hopefully I can work with Daniel or someone else from Johnson Creek Watershed to disseminate that link. And I also want to thank Tiffany, who was part of our stakeholder roundtable from Johnson Creek Watershed last semester, and hopefully she'll come again. So yeah, thank you. That's it. I am going to stop sharing my screen now.
Thank you, Julia. Sounds like a very comprehensive program. Our next speaker is Max Lambert. He recently began a position as a senior scientist with the Washington Department of Fish and Wildlife, where he leads a team studying a diversity of wildlife conservation and habitat restoration issues. He's going to be addressing the interesting question, are stormwater ponds toxic sinks or valuable habitat for amphibians?
Thanks, Bruce. Nice to have you all here, and thanks for letting me cap this off and end the day. Talking about a really fun project I initiated last year with a bunch of folks in Portland and Gresham. We kicked it off right as the pandemic started, and we still managed to get some great data off of it, despite having lockdowns and shelter in place as well. Our tadpoles were in the middle of cages and ponds. And to that, I give a lot of credit to Laura Guderian, City of Portland, and Katie Holzer, who you all know at Gresham, Lauren Chan, Pacific University, and Marissa Ekman, who really brought this project to its conclusion. We had a variety of other collaborators as well. Kelly Smalling at the USGS just did a ton of good analytical chemistry for us in these stormwater ponds and natural forested ponds in Portland and Gresham. So some really fun data. I'm looking forward to kind of showing you what we did. So we're going to talk about stormwater ponds today, which are really a broad category of created ponds in urban areas. They vary from these kind of gross, scuzzy, sedimented concrete basins that no one wants to look at, to things that are a little more like this, that are pretty artificial looking in parts, but have some nice vegetation added around, but they're still in the middle of the urban backdrop around them. Of course, now my screen's going to freeze. There we go. To ponds like this that look pretty natural when you're in the middle of them. You can see a house behind it, but they're pretty well forested and seem like a natural pond if you didn't look too far away. When we talk about urban ponds, when it comes to amphibians and other wildlife, people think about landscape heterogeneity, how broken up and developed the landscape is for allowing animals to move through it. When it comes to frogs, they're playing a literal game of Frogger to try and colonize pond to pond, which is really important for things like stormwater pond, which we actually build. How do we get animals and wildlife to use these ponds if you want to view them as habitat? The kind of other side of that when it comes to things like amphibians is we don't oftentimes think about or really test in an explicit way water quality, the impacts of pollution on the habitat quality we've just built. And with things like stormwater ponds, we build these ponds on purpose to slow water down during storm events, to not erode our landscape and not to incise our stream channels, but also let things like sediment and pollutants settle out of the water before that stormwater moves its way into streams and rivers. But by default, by engineering, these collect a ton of pollutants off of the urban landscape. Now, when you're a frog, your skin is super sensitive to pollutants. And so if you're bathing in a highly toxic environment, maybe we're creating these death traps that are not really great for them to be in the first place. Even so, there are plenty of amphibians that live in these urban stormwater ponds. And so this is one of the goals we're hoping to figure out is how toxic are these urban stormwater ponds in Portland and Gresham for our native amphibians, and how are they really dealing with this kind of pollution? Now, some of these ponds differ in their watershed size, which really can affect the amount of pollutants that show up in them. So the red dashed line here is the watershed for a pond that's the yellow star there is that pond during the dry season. It's a single elementary school plot is basically the entire watershed for this one really large pond. In contrast, the purple dot here in the far left of the screen is a stormwater pond, and the red dashed line here is the entire watershed for this one small pond, which is a humongous chunk of Gresham that crosses multiple large roads, some playing fields and things of that sort. So all of that during a storm event drags water through pipes into this one pond. And so what we did, we took embryos of this critter here. This is the red-legged frog, which is the species that's fairly common across the Northwest, but has shown pretty substantial declines in recent decades due to habitat loss. It's a pretty forest-dependent species, but it's surprisingly common in urban ponds in Portland and Gresham. And it's really great because it's a species that's common enough for us to manipulate, but also of conservation concern enough for us to really want to think about management. And it lays egg masses in these stormwater ponds that we can easily pull small embryos out and do manipulative experiments in the middle of ponds with fairly easily. So it's a really cool little critter right in these ponds that we can play with. And so what we did is we took egg masses from red-legged frogs, and we're actually able to take a handful of embryos out, not the whole egg mass, and raise them in these enclosures that are made from window screening and PVC pipe, and embed these enclosures in a variety of stormwater ponds and natural ponds, and raise these embryos from freshly fertilized eggs to metamorphosing tadpoles. That would be kind of when a frog transitions from being a tadpole to a froglet on land. So we can really get a sense using these enclosures, these experimental cages, how well water quality, the conditions of the water actually impact the embryos and the tadpoles for survival and how well they develop, how healthy they are. It's a really great way for us to do experiments right in the field, like you saw in the last presentation. And the way our experimental design worked is that we took a bunch of embryos from frogs that are living in nearby forested ponds, those that are forests within the city, but also forests on the outside of the city, and took those forested frog embryos and plopped them in multiple other urban ponds that were constructed. And we also put those forested frog embryos into all the other forested ponds as well. And those forest ponds act kind of like our experimental controls. And the great thing about these populations, they've never experienced pollution hypothetically, so they should be relatively immune to the impacts of pollution that might occur across generations that impact the health of the adults. We also took embryos from red-legged frogs that currently exist in Portland and Gresham and tossed their eggs also into enclosures into those forested ponds and into each other urban pond we were playing with. So we can get a sense of whether existing red-legged frogs have somehow have a different capacity to deal with urban water quality than forest red-legged frog populations might. And one of the unique things we did also with this experiment is we actually transplanted all these embryos from these different forest and urban populations into urban stormwater ponds where there currently aren't any frog populations living there. And this gives us a chance to see whether water quality may be one of the things that's stopping those frogs from colonizing these urban habitats. We currently don't have amphibians present, or at least not red-legged frogs. I won't get into all that data today, but I'll show you a few of the results I think are pretty fun and interesting. And this is just a quick map to show you some of the sites that we had across the city. These little green triangles are our forested control sites where we had the red-legged frogs. The yellow stars are our urban stormwater ponds where red-legged frogs currently breed. And the pinky purple dots are urban sites where there currently aren't any red-legged frogs present there. And we have really good longitudinal data showing that red-legged frogs are not present in these sites. So this is kind of the main data graph to come out of this experiment. What you see on the y-axis are the percent of the embryos that survived from being an embryo to metamorphosing tadpole at the end of the experiment. And on the x-axis, you had the land use of the ponds where the tadpoles were raised. So either you're in a forested pond or an urban pond. And I colored these box plots in based off whether the animals came from a forested pond as a source population or an urban pond. It might be kind of starkly obvious from this graph, there's really no difference in survival overall based on whether we put a red-legged frog embryo in the middle of a forested pond or an urban pond, nor whether their parents were from an urban pond or forested pond. So pretty much overall, these urban stormwater ponds are pretty decent habitat on average for red-legged frogs to develop, which is pretty cool. And I won't show data, but we have some fantastic data from the USGS measuring dozens and dozens of organic contaminants and metals. And these urban stormwater ponds are full of a pretty remarkable diversity of pollutants that are pretty much not present in the forested ponds. So there are tons of pollutants present. It doesn't seem to be a huge problem for all of these red-legged frog populations as far as survival and development of the animals go, which is pretty neat. That being said, there's some interesting variation pond to pond that I kind of want to dig into real quick to show you all. This is one of our urban ponds. This is the same elementary school I showed you previously. Pretty residential neighborhood surrounding this pond. Great looking pond. We're actually in the middle of it wearing waders. When it's snowing on you, you can see the pile of cages over there in the middle of the pond. This is kind of the same type of data I just showed you previously, but I broke it out by all the various source populations there on the x-axis that they came from, 3 forested and 3 urban. And again, the y-axis is the percent surviving. In general, this pond was great. 75% of the embryos survived to the end of the experiment. No differences really among ponds. It just seemed like everyone did really well here. So this is a great pond on elementary school's campus, and red-legged frogs love it. Now contrast this to the Brookside wetlands in Portland. The pond there is actually not the pond you're looking at. There's a series of small ponds in the forest closer to you. This is a restored area, series of great little stormwater ponds. Looks great natural when you're in it. You can see the cages in the background there, very pretty pond, full of fun garbage and needles and bread and horrible trash, and plenty of chemicals. There's actually some pretty big differences in terms of who survives. On average, roughly a third of embryos survive, but it differs depending on whether the parent frogs came from forests or urban populations. All of the forest embryos that were raised in this pond, about a quarter of them survived, whereas twice that number survived if the parents came from an urban pond. So it seems like, at least with dealing with the water quality of the brookside wetlands, that if you're from an urban pond, you're going to survive much better than if you come from a forested pond. And this is in evolutionary biology, we call this local adaptation. So somehow these frogs have managed to rapidly deal with water quality in these urban populations, which is pretty cool. I'll give you one last kind of contrast to that. And this is the Kelly Creek stormwater pond. You can't quite see the pond there, but it's in the forest. It drains a good residential area around it, but also has some water coming in from agricultural landscapes to the east. Another great looking pond, deep, tons of biodiversity in this place. It's a really cool little pond. Again, those are our 6 little cages we had embedded in it.
We have about a minute and a half.
Great. Tons of variation among the source populations for how well they did. But one of the things to kind of key in on here is that pink star on the far right, that's the Kelly Creek red-legged frogs that are from Kelly Creek and raised in Kelly Creek. And they survived worse in their own pond than anyone else did from coming from other ponds, which is pretty interesting. I won't kind of go into various reasons for this. There's a couple of different mechanisms that might cause that. But just because, it's kind of an interesting pattern in evolutionary biology and conservation to see this sort of thing happening. But even so, there's about 400 red-legged frogs that breed here every year. So it's a pretty nice little red-legged frog population, despite this weird pattern popping up. And I won't show you the data on it, but we did raise frogs again in places where there currently aren't any frogs breeding. 2 of those sites had great survival. This one site here, this is a Fairview stormwater pond. Everything died before it even got to hatching. It wasn't so much a water quality problem, but when the rains come, this thing becomes a flowing river that just covers the cages in mud. It was a pretty much a nightmare to try and get this pond to work. But ponds are variable. Some are bad, some are great. That's kind of the lesson learned. And so it kind of ended this story was these urban stormwater ponds are pretty good little urban habitat for things like amphibians. Water quality is definitely impaired, but it doesn't seem to be overwhelmingly limiting for the success of these little amphibians to deal with life in the city. And with that, I'll end it.
Thank you, Max. Lots of adaptation questions to be answered there, it looks like. So we're going to start the question and answer session. Let me pull up the questions here. We'll start with Julia Bond. The first question is, did you collect stem density of FRLA as well?
We were looking, so there's a fair amount of field data that was collected as part of this effort and looking at both overstory, but also the understory. And so as part of the overstory, yes, we were counting the number of individual ash trees that were present, as well as looking at the kind of overall height and sort of maximum minimum heights and the average height of the trees that were present in each one of those plots, but also within each one of those individual bands. So for the Oregon ash trees, yes, we were counting number of individuals.
Great, and I think we'll stick with Julia for the next 2 questions. When the emerald ash borer beetle arrives, is it expected that the Oregon ash trees won't stand a chance? Is there a risk of losing the Oregon ash species entirely? And I would ask you to also speak to what we know about relative sensitivity of the Oregon species versus the Midwestern species.
I don't know for certain how much research has gone looking into the Oregon ash species specifically directly related to the emerald ash borer, but my understanding is that it's expected to be highly susceptible to the emerald ash borer, and given that it's the main species in town, if it does arrive, the expectation is that it could be seriously imperiled or potentially driven to extinction.
Okay, and our next two questions are similar, so I'm going to combine them. Is there a recommendation, formal or informal, that new restoration plantings avoid the use of organ ash? If so, what is the current thinking about appropriate substitutes?
I don't know that there's any official recommendations at this point in time. As I mentioned before, the general consensus is that it really is more a matter of time before it arrives, as opposed to, if it's going to arrive. And so for planning for resiliency and thinking about our restoration projects and what you're going to be planting, not necessarily eliminating Oregon ash from planting pallets, but recognizing that whatever you're designing to, it is potentially not necessarily going to be present or available in the long run. So not wanting to have your planting pallet dominated by something like that. In terms of substitutes there, one of the sad or difficult things is that Oregon ash is definitely somewhat unique in terms of the niche that it occupies within our riparian landscape. It's really good in those low-lying areas, the wetlands and things like that. But potentially species like black cottonwood or red alder are ones that, if the spot and the location is right, there is the potential for those to thrive instead of Oregon ash.
Our next question is for Julia Michaels. How are reference sites viewed within the context of your applications of restoration theory?
Bruce, Julia had to leave. She had
okay.
another meeting, so unfortunately won't be able to answer those questions.
Okay, I guess we'll skip over the questions that were directed to her. This one's for Max. Were seasonal and flashy storm-related water levels relative to egg masses in the ponds recorded?
That's a great question. I think Katie Holzer, if she's on, might be able to better answer that question. I don't actually think we have a great handle on exactly the number of egg masses and what they're related to in Grisham and Portland. There's some prior data on is it a constructed pond or natural pond or something like that, and the amount of forest buffer and whether they're fish. That last pond I showed you, the Kelly Creek site, can be remarkably flashy. When Katie showed it to me, it can raise many, many feet in a good storm event, which is pretty flashy for that sort of small pond. At the same time, I think Katie's recorded something like 400 egg masses there at one point in time. And so I think there's a ton of variation and a lot of various factors that kind of contribute to whether a pond has only a handful of egg masses or a lot of egg masses.
Great. It looks like our last question is for Jason. And it's something I was thinking about as you were speaking. Should we stop coddling our trees? The question is, did you conclude that people should not water their mature trees during the summer?
I would say our data wouldn't support that definitively, enough to give an actual policy recommendation on that. It's definitely an intriguing relationship that we're seeing, and we're going to try to follow up on that more by, in future field seasons. I think that it was quite surprising finding for us, but it's really hard to tease out some of these possible confounding factors based on different management strategies of street trees versus park trees, and where we're seeing watering much more dominant in parks versus streets. So there's a number of factors at play, and I would not give that as like a firm recommendation. But I do think that there's probably something to be said that, in nature, trees don't get, artificial watering. They're in their life histories, they're going to withstand some very difficult drought years. And that probably, either culls the vulnerable ones or provides some long-term adaptation. So unless you're talking about, non-native species or things that are on the brink, there's a whole other conversation we can have about climate change and Western red cedar and what's happening with that, because it's in a lot of trouble as a species. I know that the management community is talking about more deliberate efforts to increase watering for red cedar in parks. But I think the jury's still out overall about whether watering in urban areas is bad for trees. Definitely do it in the first few years, though, until they establish.
Hey, Bruce, I brought Katie back up. Katie, would you like to address that last question?
Sure, I'll just say a couple words about the flashiness, that it can definitely be a problem. The stormwater ponds tend to be a lot flashier when it rains than a natural pond since the water's coming in quickly. The biggest problem we've seen with it is frogs often like to lay their eggs right after it's been raining. So if that pond is really full up because it's been raining hard, they might lay their eggs in the plants that are currently underwater. And then over the next day or two, as that water comes down, the eggs might get stranded on the side. So that's something to think about sort of if you're designing a pond that might get frogs in it. But other than that, it's the biggest issue we've seen.
Great, thank you, Katie. I would like to thank all of our panelists. Great talks, really appreciate it. And Daniel, I'm going to turn it back to you.
Okay, thank you very much, Bruce. And thank you, Julia, Jason, and Max for the second session talks. Before we completely leave here, just a couple things for everybody. Number one, as I mentioned earlier, this is being recorded. This is going to be up on YouTube. Give me about a week. The other thing is, just to let you know, some of you who may have registered at the last minute, earlier this morning, I sent out a copy of the program, which includes the bios of the speakers, the abstracts, and the titles. If you did not get that, please email me at daniel@jcwc.org, and I'll be happy to send that to you. The other thing too is, in addition to getting all the symposium up on YouTube, eventually a week or two, we will have copies of as PDF files on our website for all the science symposium presentations. So if you want to go back and review something you're interested in, please feel free to come look at that on our website, but give us about a week or two. So with that, I would like to say thank you everyone for coming today, and look forward to next year in the 8th annual Johnson Creek Science Symposium. And if you hear of anything that would make for a good presentation, please let us know. So thank you very much.